Part 2 of Lesson 2 of Chapter 2 is more on polynomial functions. Example 4, we're going to state the number of possible real zeros and turning points for this polynomial function. This is a fourth degree polynomial function with a leading coefficient that's positive, so therefore it's going to be a touchdown guide like you can see in the graph. Both ends are going up. It says then determine all the real zeros by factoring. So there's a rule basically that says every fourth degree could have at most 4 real zeros. Because it's a fourth degree polynomial, it could have 4 possible real zeros. Now when you look at the graph, how many times do you see it cross the x-axis? Only twice. Once there, once there. So there is actually only 2 real zeros. And so now to find those, we have to do some factoring. On this one, what we can do is we can set up 2 groups of parentheses. We'll need an x squared as our first terms, and we'll need to have a minus 4 and a plus 1. Okay, now from there, the x squared plus 1 can't be factored any further, but the x squared minus 4 could be factored into x minus 2 and x plus 2. So there's the factored form, and then the actual real zeros. Would be at plus or minus 2, and that corresponds with the graph that we're seeing. Next example, same kind of problem, same direction. State the number of possible real zeros. Well, this is a fifth degree polynomial. So that means that there's 5 possible real zeros. If we look at the graph, we can see that it does cross the x-axis only 3 times. So therefore, there are only 3 real zeros. And to find those, we're going to find those by factoring. So on this problem, I can start off by taking an x out of everything. And then after I take an x, then I can make my 2 groupings. Got to have an x squared on the front of both of them. I'm going to need a minus 8 and a plus 2. Okay, the x squared plus 2 cannot be factored any further, but the x squared minus 8 could factor into conjugates x minus square root of 8 and x plus the square root of 8. Therefore, our real zeros would be 0. That's from this x right here. This factor would produce imaginary zeros, so we don't need to worry about that right now. And then this would be positive square root of 8, and this would be negative square root of 8. And that corresponds to what we see on the graph. The square root of 8 is pretty close to 3, but not quite. It's like 2.9 approximately, and negative 2.9, and you can see that on the graph. Example 5 now says state the number of possible real zeros and turning points. On the last problem, we didn't have to do turning points, so they're just adding to our directions. Well, it's a fourth degree polynomial. So that means we have 4 possible real zeros, and that means we would have 1 less 3 possible turning points. There's always 1 less than its degree. Then determine all the real zeros by factoring. Well, if we look at the graph, we can see that there is 1, 2, and then this 0 right here, because it touches the x-axis and not crosses it, it's counted as a repeated 0, so that counts as 2. Okay, so finding those, we would factor negative x squared out of everything, leaving us with x squared plus x minus 2, and then from there we could factor that into x plus 2 and x minus 1. So our real zeros are found from the factors. We get 0, we get negative 2, and we get positive 1. So we actually have 3 real zeros, but one of them is counted as a double or a repeated 0, a double root, and that is at 0. Example 5, same direction. State the number of possible real zeros. Well, this is a third degree polynomial. So therefore we have 3 possible real zeros. Possible turning points. There's always one less. So that would be 2 possible turning points. And now we look at the graph and you can see that there are actually 1, 2, 3 real zeros. And so to find those, we'd factor. I'm going to start off by taking a negative 2 out of everything. Sorry, negative 2x out of everything, leaving me with an x squared plus 2x minus 8. And then to factor from there, we have a plus 4 and a minus 2. And so my real zeros are at 0, negative 4, and positive 2. Lastly, example 6 gives us a function. This is in a factored form, and it says part A, apply the leading term test. Now, the leading term test, there's nothing to write down for that. It's simply understanding what's the graph going to look like. We can see the graph, and you can see that it's a touchdown guy. Both ends are going up. And you should be able to figure that out by looking at the equation. Okay, if you guys look at this, how many x's do we have? If we got rid of all those parentheses, we'd have 1, 2, and then 3, 4, because we got a square on that x minus 1. So it's a fourth degree polynomial. The leading coefficient would be a positive 1, actually be a positive 2. So that's why it's a touchdown guy. So that leading term test is just understanding if it's going to be a touchdown guy, gorilla guy, disco guy Randy, disco guy Larry, what's it going to look like? Part B, determine the zeros and state the multiplicity of any repeated zeros. So on part B, since it's in a factored form, that makes it easy to find the zeros. We're going to have a 0 at 0 from the x. We're going to have a 0 at negative 3 over 2 from the factor of 2x plus 3. And we're going to have a 0 at 1. And this one has multiplicity 2. It's a repeated 0. And notice on the graph, what happens at x equals 1? It touches the x-axis. It does not cross. Part C, find a few additional points. You don't have to do that. You can thank me later. And then graph the function. You can just do that with the graphing calculator. So really all you're doing on these is taking the equation and identifying the zeros and stating the multiplicity of any repeated zeros. So number 6, it gives us an equation. I do have it graphed already, but the graph sometimes is misleading. If we look at this equation, how many x's do we have? It looks like we got 1, 2, 3, 4, 5. Because we got that 3x minus 1 raised to the third power. So since it's a fifth degree polynomial, it should be a disco guy. The leading coefficient on this would be a negative 6, and so that's why it's a disco guy Larry. Left side is going up right here, right side is going down. Now when you look at the graph, it appears to cross the x-axis once, and then it kind of looks like there's a repeated 0 that doesn't cross the x-axis right here, but again, that part of the graph is a little bit misleading. If we look at the equation, that'll give us our zeros. We have a 0 at 0, and that's from this part of the equation. We have a 0 at 4, that's from this part of it. And we also have a 0 at positive 1/3. And that has multiplicity 3. Okay? So the reason the graph is misleading is because we have a 0 at 1/3 and also at 0, and those are pretty close together. So this graph right in this area right here, it actually drops below the x-axis if we were to zoom in on that, and then it comes back up. It drops below at 0 and it comes back up at 1/3. Last example, same directions. Apply the leading term test. Take a look at this. If we this isn't in a factored form. So it's a third degree polynomial. Leading coefficient's negative, so it should be a disco guy Larry. And as you can see on the graph, it is. So now we got to find the zeros. Well, this isn't factored. It'd be much easier to find the zeros if it was factored. So let's take a negative x out of everything. And then from there we can continue to factor. And now that we have it in a factored form, it's easy to identify the zeros. And they are at 0, 4, and -2. And none of these have multiplicity of 2 or 3. And if you look at the graph, that corresponds because it crosses the x-axis at 4, it crosses the x-axis at 0, crosses at -2. If it has multiplicity 2 or 3, it does some unusual behavior at the x-axis.